Hi, my name is Kathleen Given, and I'll be starting our presentation of shape-adaptive composite foams with high expansion and absorption used for massive hemorrhage control and irregular wound treatment, based on a paper by Wang et al. In 2018. So, why is this important? Trauma and hemorrhage are a global health problem impacting both civilian and military populations around the world. Hemorrhage in particular is responsible for 30 to 40% of severe trauma deaths and caused 5.8 million deaths last year. For this reason, developing effective hemostatic materials is critical. However, the current field has some serious limitations. There are two classes of hemostats, inorganics and organics. Inorganics can lead to thermotissue injuries by the exothermic reaction they produce and create high immune response owing to their poor biocompatibility. They have also presented limitations in achieving the rapid hemostasis necessary. Organics cause allergic reactions and nerve compression through their excessive swelling, and have proven less useful for irregular, deep, or penetrating wounds with massive hemorrhage, such as those caused by minor caliber weapons, shrapnel, and devices. It is an attractive candidate due to its excellent biocompatibility. Additions to the alginate have also been feasible and beneficial. For instance, by adding metal cations to interact with the glucuronate blocks in alginate, polymers have formed with a beneficial egg box structure. Overall, alginate-based composites have shown to have excellent biocompatibility and promotion of wound healing and overall hemostatic function. However, poor chemical stability and weak mechanical strength restrict wider applications of alginate-based composites, particularly in use against massive hemorrhage. The aim of this project was to develop a novel hemostatic and shape-adaptive composite alginate form. Recent research indicates that by using different cross-linking agents and changing the method of synthesis, composites could maintain the important porous structure for absorption while obtaining better hemostatic properties through increased expansion and absorption than the current hemostatic agents. The hypothesis of this paper was that cross-linking PVA and CaSO4 into the alginate matrix would produce a highly hemostasis-inducing and shape-adaptive polymer. This would occur through the combination of multiple hemostatic mechanisms. The composite foam's porous structure could quickly absorb plasma and concentrate blood cells, while the negative charges on the alginate would stimulate the surface of the PACF. Additionally, the PACF's flexibility and deformability were maintained in the alginate matrix.
Hi, I'm Aurora, and I'll be introducing the methods and different techniques used in this paper. All results reported were shown as mean plus or minus standard deviation, and the significance was determined through ANOVA. Two types of samples were tested in this experiment. PVA was cross-linked by glutaraldehyde to form PVA foam, as was a PVA alginate composite, which was then molded and freeze-dried with varying alginate mass fractions. For physiochemical characterization, the authors determined surface structures through infrared spectrometry, observed surfaces through optical microscopy, and measured surface roughness with confocal laser microscopy. Additionally, they characterized morphology and microstructure with scanning electron microscopy, or SEM. The contact angle was measured from water dropped on the different materials. To measure the material's ability to hold liquid and expand, the samples were soaked in PBS for an hour. The weight and volume before and after was measured to find liquid adsorption and volume expansion. A 0.1 Newton trigger force was applied before the expansion test began. PBS was added to the sample and the buoyancy forces were measured continuously for an hour. The expansion force was taken by subtracting this force from the raw force. Fibrinogen solutions with different concentrations were prepared using PBS in order to determine the FIB adsorption. FIB aqueous solutions and discs of PF or PACFs were mixed. The adsorption of FIB was determined by UV-vis spectrophotometry. The morphologies of the adsorbed FIB on the surface of samples were observed by SEM. Platelet adhesion in vitro was analyzed by suspending platelet-rich plasma. SEM was used to observe the morphology of the adhered platelets, which were fixed using glutaraldehyde solution and dehydrated through ethanol soaking and freeze-drying. The platelets in the sample were quantified by measuring lactate dehydrogenase release from the lysed platelets. To evaluate blood clot formation and strength in vitro, citrated whole blood was mixed with the different samples in plastic vials. Thromboelastography was then performed to evaluate the initial fibrin formation time, clotting time, and maximum strength of the formed clot. Additionally, the authors had whole blood samples interact with the materials. The blood coagulation time was measured, and the hemoglobin in the red blood cells was dissolved. A microplate reader then measured the absorbance of the hemoglobin to determine clotting levels of the PFs and the PACFs. In vivo hemostatic performance of 40% alginate composite foam was studied using a hemorrhaging liver mouse model, as well as the swine femoral artery gunshot injury model. In the gunshot model, the vessel bled freely for 30 seconds. Then PACF particles were applied quickly and as thoroughly as needed to stop the bleeding. The injury was observed every 10 seconds, and the hemostatic time was recorded. The blood flow, blood vessels, and morphology of the samples were computer monitored.
Hi, my name is Karen Dong, and I'll be presenting the results section, starting with the physical properties. First, the different PACF formulas were visualized using surface morphology, and you can see the visible calcium alginate particles in A and B. And then the PACFs were seen to have larger contact angles with water and having lower hydrophilicity. But all were still lower than 90 degrees, so were hydrophilic overall. Surface roughness increased with alginate concentration, and therefore surface area increased, contributing to platelet and plasma protein adhesion, and surface potential decreased because of increasing carboxyl groups from alginate, going from -13 to -32 millivolts. For liquid absorption, 15 milliliters of liquid could be fully absorbed by the PACF within 20 seconds, the capacity ranging from 1,792% to 1,141%. Volume expansion rate average was 2,000% in figure C, and expansion force ranged from 1.5 newton to 8 newtons, which is sufficient radial force to apply pressure to wounds from within. PACF increased fibrogen absorption, and protein fibers were seen on the surface of the PACF as well. There's no visible platelet adhesion on PF, but PACF3 and PACF4 had higher alginate and higher platelet adhesion. The solutions were also tested for red blood cell leakage, which can be visually seen and tested using spectroscopy for the absorbance of hemoglobin. And it was shown that PACF3 and 4 trapped red blood cells better and encouraged clot formation. The PACF was also tested in vitro and in vivo. In vitro, it was tested using blood from a rabbit ear vein, and the clotting time was compared for the different alginate content samples for PACF, as well as compared to different other market clotting factors that are already generally used. In both cases, PACF had 3 and 4 had the shortest clotting time. In vivo, 2 different models were used, a hemorrhaging liver mouse model and a swine femoral artery gunshot model. For the hemorrhaging mouse model, much less blood was shown volume-wise on the stained filter paper in A2 and A3. And then for the swine femoral artery gunshot model, the injury leads to 100% mortality if not treated, but once the PACF was placed in the injury and blood absorption and clotting were observed, none of the swine died.
Hi, my name is Bridget Stanton, and I'm going to be covering the discussion portion of this presentation. I'm going to be talking about the advantages of the PACF composite foams. The first advantage of this brown material is the ability to have a fast and high absorption rate. This is crucial in order to rapidly stop bleeding and hemorrhaging in the battlefield, allowing for more time to reach medical attention. The average liquid absorption rate of the composite foams was more than 1,200%, which is favorable for rapidly absorbing plasma. Experimental results showed that the PACFs could be delivered into the wound cavity in the shape of small particles and undergo more than 20 times its volume expansion to fill large cavities, which is more than 10 times larger than the common hemostatic materials on the market. The second advantage of the PACFs is the charge simulation. The charge simulation is related to factor 7, a serine protease zymogen in the plasma that interacts with the negative charged networks of the PACF. The activation of factor 7 diffuses into the plasma and triggers the intrinsic pathway of blood coagulation. The PACFs also has the ability of releasing calcium 2 ions from the network into the blood. The calcium ions not only contribute to the activation of the intrinsic pathway, but also help to produce the thrombin to generate fibrin clot. The surface effect is a third important advantage of the PACFs. This is attributed to the porous surface of the PACF coupled with the high roughness, which induces the fibrogen absorption and blood cells adhesion, thereby promoting the formation of the thrombus in seconds. The fourth and last advantage is the expansive force of the PACFs, which averaged a total of 6 newtons of pressure into the large vessels to help stop bleeding. As for the limitations presented in this research, the storage of the biomaterial is crucial. The composite foams must be kept in a dry area in order to optimize absorption, which may be difficult in a battlefield environment. Also, the access to freeze drying may be difficult in this environment, therefore needing all the materials to be transported to the specific location. In trials, we realized that there is an inability to precisely control the amount of swelling of the composite foams, which may be difficult and detrimental to tissue healing. In terms of further research and steps moving forward, we believe that improving efficiency is key. The efficacy of the material has not been tested by vigorous clinical trials, and we do not have a very good understanding of the long-term effects when it comes to tissue healing. And as part of our overall thoughts, we believed that this research looked very promising and has a great outlook for future things to come. As for our overall thoughts for the foam composites, we believe that the direction of this research looks very promising. The addition of the alginate into the composite foams is a better solution to the problem, and we hope to see more progress in the future to help work on the limitations.
Thank you so much for listening to our presentation today.